Alright guys, so we've had some practice with organic chemistry, we've been naming, we've been moving the molecules apart and looking at different isomers, and for some weird reason we're now going to take a slight diversion away from that, and I'm going to tell you a little bit more theory, and I don't know why it's here, but it is. So I'm just going to spend a bit of time explaining what you need to know about this subject, and if you need to know more and want to know more, I can definitely explain it, but the questions that you guys get asked are usually straightforward if you know the rules of what is going on. So again, I'm just going to stick to these are the rules, these are the things you need to know, and I will try not to drown you in theory. So there's going to be a lot of new words and terms here, so please bear with me and I will explain. So you can see over here, E1.5, sigma and pi molecular orbitals in alkanes and alkenes. This goes a little bit above the specification, but for some reason they want you to know this. I'm not sure why. Let's remind you about a covalent bond first of all. So a covalent bond is a sharing of two unpaired electrons, and what this actually looks like is more like an overlap of orbitals. Let me explain. I think the diagram below is actually quite good. Yes, I did make it, so bear with me. So we've got a hydrogen, and we're going to have another hydrogen. And let's give that hydrogen its one electron. Let's give this one its electron. Probably should have put them on the same side. Let's do that. So what we're looking at is when we form a covalent bond, we know that we have a shared pair of electrons. Looks a little bit like that, and we get our hydrogen molecule. Now, in reality, this is more like an overlapping of orbitals. So if you can see this red cross, so this is going to be our electron. Now this actually whizzes around this hydrogen basically at the speed of light, and it's very, very hard to determine exactly where it is. You can say how fast it's going, but then we don't know where it is. But then if we know where it is, we don't know how fast it's going. That's just weird. But I'm going to replace that X with this. So this sphere, remember it's an s orbital, so it's a sphere. This is going to contain an electron, and there's a 95% chance I'm going to find it in there. That's our definition from orbital back from like week 1. And I'm going to stick an electron there so you can see at some point we stop time, we see it's there. The blue one, I'm going to do the exact same thing. So let's get rid of this, and this blue one is now going to whiz around, again near light speed, and all of a sudden we now have an orbital that looks like this, and I'm going to stick its electron there. In fact, just so I can make things weird, I'm going to put its electron over here. Now, when these two come together, we are going to share a pair of unpaired electrons, but we're also overlapping orbitals. So this is another way that we're going to now look at this. So when these overlap, just like that, you can see they come together, and there's the overlap there. And now we have this guy, which is our hydrogen molecule, which is our H2. So they're the same thing. I'm just trying to show the covalent bond in the middle. When we overlap in this way, the bond, this bond that's formed, we actually call this a sigma bond. So it's like weird, like an O with a hat, and we call this a sigma bond. Now, to simplify things for you guys, all single bonds, so this is a single bond, every single bond is a sigma bond. And the way this happens is by the type of overlap. So this is your mark scheme, this is the detail I'm going to go into. We have something called a head-on overlap. That will form a single bond, which we call sigma bonds. So just with this diagram, just like before, I think it's going to fall apart now. It has, I've lost its electron. But when these come together, we see that they're coming together head-on. So if you imagine like cars, they're coming and they're crashing like this. So that is what we call a head-on overlap. They come together, they overlap head-on fashion. So that is a head-on overlap that forms a single bond that is forming a sigma bond. And all single bonds are sigma bonds. Let's have a look at the other scenario. We have something called a side-on overlap, and we find those in double and triple bonds. And we call this bond a pi bond. Now, I don't want to go into the diagram too much, but you can see some of the diagrams down here. If you're really interested, I can show you exactly where this comes from. But I would rather just give you the marks and not worry too much about the detail, because the theory behind it is quite crazy. Whenever you see a double bond, I would like you to know that every single bond is a sigma bond. So every single bond, single 1, 2, 3, and 4, there we go. They're all single bonds, they're all sigma bonds. When we have a side-on overlap, we've still got a single bond between C and C. It's right here. That's our single bond. However, because there's another bond, we call the whole thing a double bond. Just like that. That green one is our pi bond. So it looks like this. We call it a pi bond. And the way this one forms is due to side-on overlap. Now you can use flashcards to remember this. I think this is the easiest way to go around it, but all single bonds are sigma bonds and all pi bonds have one sigma bond and one pi bond. And you can see in the diagram below, this is kind of how it happens. These are the p orbitals. So if you go back to the electron configuration of carbon, you'll have p orbitals that don't necessarily have electrons in them when you hybridize them, but it doesn't want me to teach you that. And I said I would avoid the theory, but we have these orbitals over here. They overlap and they form these pi bonds above and below. This pi bond above and below is one half of a pi bond, and that's the other half of a pi bond. So the two lobes is one pi bond, and this is kind of how it forms. I'm not quite sure how they may ask you this question. They could ask you to draw something that looks like this. So I would practice that in your cards, and if you want me to teach you some of the more theory, I definitely can. But I think my video when I taught hybridization, it took me 2 hours, and I don't think you want to sit here for 2 hours. This table down here is going to summarize everything that you need to know. Learn this table inside out and you should be there with the majority of the marks. So single bonds are head-on, sigma. Double bonds is a head-on plus a side-on, which is sigma and pi bond. And then a triple bond is going to be one sigma bond and two pi bonds. These are some of the notes. So sigma bonds form direct head-on overlaps. They create very, very strong bonds. And pi bonds are side-on overlaps. And they're not much overlap, so they are actually weaker than a single bond. However, sigma bonds, there's only one, and a double bond is stronger. So even though a pi bond is weaker, there's two bonds, and that makes them stronger than one. Single bonds have only sigma bonds, and they're allowed to freely rotate, so they can spin around this single bond. However, a double and triple bond restricts that rotation because we can't break this lobe. So the lobe, if we try and twist it, it won't let us twist it, it won't break, and that's why they're restricting that rotation, and they form stereoisomers. Right, what I'd like you to do is you can use the notes here as well, but I would like to have a go at answering these multiple choice questions. There's 3, have a quick go at them, and this should be as far as you need to know on this subject.